take a look at this equality. On the left-hand side, you have the summation of I times 2 to the I. I starts from 1, goes to n plus 1. You want to show that the summation of these terms is equal to n times 2 to the power n plus 2 plus 2. We're going to apply the method of induction. Suppose Pn is a property. This is a property. Left-hand side is equal to right-hand side. That is defined for integers n, and let a be a fixed integer. Suppose the following two statements are true. P at a is true. A is usually the smallest value in the domain. The second statement is for all integers k more than or equals to a, if pk is true, you're able to prove that pk plus 1 is also true. Then you can conclude that this Pn is true for any n more than or equals to a. So let's see. We're going to start by plugging the smallest value from the domain. Since n is more than or equals to 0, we're going to plug in 0. 0 on the left, 0 on the right. For 0 on the left-hand side, the summation becomes the summation I starts from 1, goes to 0 plus 1, which is 1. I times 2 to the power I. This is basically plugging 1 for I, because I starts from 1 and stop at 1. So wherever you see I, you're going to substitute 1. You get 1 times 2 to the power 1, which is 2. This is your left-hand side, this guy here. Right-hand side is easy to work with, because you only need to plug in 0 for n. 0 times any number is 0. So you end up with 2. You have 2 on the left-hand side and 2 on the right-hand side. 2 and 2 are equal to each other, so we're done with number 1. P of A is true. Now suppose Pk is true. We're going to show that Pk plus 1 is also true. It means that if I plug in k for n, I have a true statement. Just want to show that, hey, if I continue plugging k plus 1 for n, that statement is going to be true as well. So let us simplify as much as we can. This is P of k. I start from 1 to k plus 1 of I times 2 to I is equal to k times 2 to k plus 2 plus 2. We want to show that this guy is true as well. We want to show that wherever we see n, we plug in k plus 1, this statement is also true. So let us simplify as much as we can. I starts from 1 and goes to k plus 1, which is k plus 2. I times 2 to the I. And on the right-hand side, wherever you see n, we're going to substitute k plus 1 for it. This is n that becomes k plus 1. 2 to the power n plus 2, which is 2 to the power k plus 1 plus 2, plus the constant 2. Again, we're just doing algebra here. We just simplify this guy into a nicer form. I start from 1 to k plus 2. I times 2 to the I is equal to k plus 1 times 2 to the power k plus 1 plus 2, which is k plus 3 plus 2. Again, our goal is to show that this statement is true. To show that this statement is true, we're going to start by looking at the left-hand side. The left-hand side says, hey, I have I from 1 to k plus 1 plus 1, which is basically can be divided up into I start from 1 to k plus 1, I times 2 to the I, and if I plug in the last term here, I get k plus 2, 2 to the power k plus 2. Again, we are trying to write k plus first term separately. You have k plus 1 plus 1. It means that k plus 2, and the last term is going to be k plus 2, 2 to the power k plus 2. This is your last term. Very good. By inductive hypothesis, we know that this statement, this summation, is nothing but k times 2 to the power k plus 2 plus 2. And you're going to copy down the last term here, k plus 2, 2 to k plus 2, which is going to be just copied down here. Now, what you can do a little bit of algebra here, everybody. How to do algebra? Well, first of all, this term and this term here, they have 2 to power k plus 2 in common. So you can factor out 2 to power k plus 2. You're left with k plus k plus 2. What's left? One constant is left, which is 2. Very good. Now, k plus 2 is 2k plus 2 times 2 to power k plus 2 plus constant 2, which is basically, if you factor out 2, get k plus 1 times 2 times 2 to power k plus 2, which is 2 to power k plus 3, and you have a constant 2, which is basically the right-hand side. Let us take a look at our previous page. We were trying to show that the summation of I starting from 1 to k plus 2 of I times 2 to the I is k plus 1 times 2 to k plus 3 plus 2, which is what is shown here on the last step. So let's take a look at the summary. We have Pn. We start by showing that P sub 0 is true, and then we plug in K, and we assume that this statement is true. We show that it's true for K plus 1. It means that we show that left-hand side is equal to right-hand side. So by the method of mathematical induction, we show that this statement is true all the time for n more than or equals to 0.